I welcome all of you to the class. This is our first class on the kinetics of rigid body in 3 dimensions. Prior to this, we had discussed a video in which a rigid body known as gyroscope was briefly discussed. In discussing the gyroscopic motion, we were trying to understand that sometimes there are motions in a rigid body which seem to be defying the fundamental laws of mechanics. And understanding the motion of these types of rigid body is very important because of their physical significances or their applications in the mechanical science. We talked about a rigid body which is known as gyroscope last time, and when the gyroscope was at rest, when it did not had any rotational motion, it was not balancing, it was falling under the influence of gravity. But giving rotation to it, making it rotate about some axis, it was defying gravity and it could balance itself against the gravitational forces. So if a rigid body like this gyroscope, which we discussed in the previous video, is balancing against the force of gravity, it means some forces are created in it that are actually nullifying the effect of the gravitational force. Okay, number one. Number two is that if we are asked to account for the equations of its motion, what are the equations of motion of such bodies, or the bodies which have a three-dimensional motion, or force analysis of such bodies? So understanding of their fundamentals becomes very important. Okay, that's what the fundamental theme of kinetics of rigid bodies in 3 dimensions is. As we go ahead in kinetics of rigid bodies in 3 dimensions, we'll be talking about force, angular velocity, angular acceleration, torque, moments, angular momentum. We'll be talking about impulse, momentum, work, energy, but in 3 dimensions right now. And very soon that we'll realize the importance of these when we try to understand the physical significance of the equations provided by the kinetics to the mechanical systems like the landing gear of an aircraft and the nature of forces created on it. That will be quite a fascination for us in understanding it. So we begin our journey of kinetics of rigid bodies in 3 dimensions by first of all understanding the angular momentum of a rigid body in 3 dimensions. As far as the angular momentum of rigid bodies is concerned, if we say, for example, assume that we have a rigid body, let's suppose we have a rigid body and we represent a rigid body by beta. This is a rigid body. And let's suppose we have a ground frame of reference, okay, which we have been defining by J. Let's suppose there is a point O that is the origin we represent in this ground frame of reference. Okay, this is the origin of this ground frame of reference, and let's locate a point. Let's call this as point P, which is a point of on this rigid body. Okay, let's say for example, this rigid body is having planar motion, and we represent one more point on this rigid body, and let's suppose this point is having very small mass. Let's call this as dm. This is a small massive point having mass dm. Dm is the mass of this point, and we assume that this point P is having a radius vector of this mass from point P is represented by the radius vector r. R is the radius vector which represents the position of the small point having mass dm from point P of this rigid body. Okay, fine. This rigid body is having some motion. As this rigid body is having some motion, if we focus our attention on this point having mass dm, then essentially in the overall motion of this rigid body, this dm must be traversing along some path. Let's suppose it is traversing along some path Let this be the path. That is, when this rigid body is traveling and we focus our attention on this mass, let's suppose this is the path that this dm has traveled all across. Fine. Then this dm will have some velocity, and let's represent that velocity by, let's say this dm is having velocity, and we represent this velocity of this dm by a vector called vector v. Vector v represents the velocity of this particle, okay, of mass dm. We represent it by vector v. Fine. Let's suppose an observer in the ground says, by the way, as far as this velocity is concerned, this is velocity of this point, okay, with respect to point P. Okay. Now, say for example, a person in the ground frame of reference is telling us that this rigid body is having rotational motion. It's having rotational motion. Okay. So if we draw the radius vector, if we happen to draw the radius vector from this point O to this small mass dm, and let's call this radius vector as r0. R0 is the radius vector drawn from point O of the ground frame of reference to the mass, small mass element dm in the beta frame of reference of the rigid body. Let's call this as R0. Fine. Now the ground frame of reference, an observer says that this rigid body is having rotational motion and says that its rotational motion is omega. That is, omega is the rotational motion of beta with respect to ground. Okay. Omega is the rotational motion of this beta with respect to the ground. Okay. Now, as we go ahead in defining the components, let's suppose that we begin by introducing a system of rectangular axes, x-axis, y-axis, and z-axis, which have their origin at P. That is, I mean to say, let's suppose we define our x-axis. Let's say this is our x-axis having origin at P. Let's call this as our x-axis. Okay. And we have an y-axis, say for example like this, and we have a z-axis like this. Okay. So as far as the origin coordinate system is concerned, we are assuming that our coordinate system is itself lying in the rigid body. Okay. And it's lying at point, its origin as point P. We call this as x-axis, we call this as y-axis, we call this as y-axis, and we call this as z-axis. Fine. Okay. Now, as far as this angular velocity is concerned, this angular velocity, um, omega, angular velocity omega of beta with respect to the ground frame of reference can be written as this angular velocity of the body. Now, we are in three-dimensional kinematics. We are discussing the three-dimensional kinematics. The rigid body will have the rotational motion, but a rotational motion, like other motions, will be like the three-dimensional rotational motion. It will have the components along x-axis, a component along y-axis, and components along z-axis. What does that mean? That means, like in the previous case, we had a gyroscope. Say for example, we have a rigid body like this. Okay. If this rigid body is rotating about this axis, then its angular velocity, if this rigid body is rotating about this axis, then we say its angular velocity is allotted or aligned along this axis. Now, if this rigid body is, apart from rotating along this axis, is also rotating along this axis, then we say that its angular velocity is aligned along this axis. Okay. Now, in three-dimensional case, the case is like the rigid body is having motion, rotation along three axes. Its angular velocity is along three coordinates, along x coordinate, along y coordinate, and z coordinate. This w, if this happens to be along three directions, if it is having three components, then its component along x-axis can be written as omega dot I. The dot product of this omega with a unit vector along x-axis along I cap. Omega dot I gives the magnitude of the angular velocity along x-axis, and this gives the direction, plus omega dot j, j cap, plus omega dot k into k cap. These are the three components of this angular velocity. This is component of angular velocity along x-axis, component of angular velocity along y-axis, component of angular velocity along z-axis, which we write as omega dot I gives the component of angular velocity omega along x-axis. We write this as omega x. So this is omega x I cap plus this is omega y j cap plus this is omega z, that is component of angular velocity along z axis. This is omega z k cap. These are the three components. Okay, let's not call this as equation 1, let's call this as our equation 1. The body is having angular velocity components along all the three directions. Okay, now we can also define the radius vector r. This radius vector r that we have drawn, this is the radius vector drawn from point O, point P to the particle having mass dm. Therefore, it will also have three components: component along x-axis, component along y-axis, component along z-axis. We can write this as, let the component of r along x-axis be x, so we write this as xi. Let its component along y-axis be y, we write this as yj cap. And let its component along z-axis be z, so we write this as zk cap. These are its three components along x-axis, y-axis, and z-axis. Call this as equation 2. Okay. Now, what we define? We are defining we are defining this an important physical quantity, what we call as the angular momentum. We know if we happen to calculate the angular momentum of this rigid body beta about point P, so we write angular momentum, angular momentum, angular momentum of rigid body beta about angular momentum of the rigid body about point P. Angular momentum of this rigid body about point P can be written as, we know it's written as h subscript P, angular momentum of rigid body about point P, is equal, the expression for it we know is equal to integral of r cross VdM. Okay, we have already discussed it in the previous lectures. VdM represents the linear momentum. Linear momentum cross product with the radius vector gives us the angular momentum. Okay, this is the angular momentum of this entire rigid body about point P. Let's call this as equation. We call this as equation 3. Fine. Now substitute the value of r and v. Okay. Now what is v? V is the velocity of this body. Okay, v is the velocity of this point P, and this velocity is, v can be written as, we can write v from kinematic equation. V is equal velocity v of particle dm, which is at a radius vector r, is equal to velocity of point P plus angular velocity of the vector drawn from P to the particle. Okay, that is that is omega cross r. Okay, r is the radius vector. This equation we know, this is from the kinematics. Let's call this as equation 4. Now this is not minus, we need to correct it here, this is plus. Okay, so this, now in this equation substitute the value of r from this equation, substitute the value of v from this equation. Okay, and let's perform the cross product. So as we went on to to find the cross product, what we will obtain, we'll obtain the expression as, the expression will be angular momentum about point P is equal to integral of r cross v dm, which is equal integral of r cross v, which is equal vp plus omega cross r, and we have our dm. Okay, so that can be written as, this can be written as integral of r cross vp, r cross vp, r cross vp dm plus integral of r cross omega cross r dm, r cross omega cross r cross omega cross r dm, which can further be modified as, this equation can be simplified now as, can write this as, this can be written as integral of r dm, r dm we can write like this, cross product with vp plus integral of r cross omega cross r cross omega cross r dm, this equation. Now if we look at this equation, uh, r cross dm cross vp, okay, as far as vp is concerned, well, vp is the velocity of point p. Okay, this is, we know this is known to us. Okay, now as far as r cross integral r cross dm is concerned, integral r dm is concerned, we are bringing this dm inside and cross product with vp. Okay, now very important to understand is first this integral r dm. Okay, now if you recall from the previous cases when we are talking about the angular momentum in 2 dimensions in kinetics, in the initial classes, at that time we said that as far as the RDM is concerned, from point P to the center of mass, we write the distance R PC. The distance from point P to the center of mass of this body is written as integral of RDM, integral RDM divided by integral dm. This is quite known to us, and this is what we call as the definition of center of mass. This is how we define the center of mass or center of gravity of a rigid body, that the coordinate, the radius vector of the center of mass from any point P to that very center of mass C is given as integral RDM divided by integral dm. Integral dm essentially is equal to the total mass of this body. So we can, therefore, this integral, if we cross product, integral dm represents the total mass of this body, that is m, and rpc represents the vector drawn from point P to the center of mass. Point P, let's suppose the center of mass is somewhere here, so this represents the rpc vector. Okay, will be equal integral of r dm. Let's substitute for integral r dm, therefore we can write this as, this is integral r dm. In place of integral r dm, in place of this integral r dm, we can write as m, mass of the rigid body, multiplied by rpc. Okay, cross product with vp. Okay, cross product with velocity of point p plus the entire expression, that is integral of r cross omega cross r dm. Fine. If we go ahead and again try to simplify it, and now we can furthermore play with it. As far as this expression is concerned, this is r cross omega cross r. Okay, this is a cross b cross c. We know from the earlier classes of vectors. As far as A cross B cross C is concerned, this identity should be well known to all of us, that the vector A cross B cross C, A cross B cross C is equal to A dot C, A dot C, A dot C multiplied by B, A dot C multiplied by B minus A dot B multiplied by C, A dot B multiplied by vector C. This is an identity that we will be substituting in this. Okay. So what expressions we'll get? Well, the expressions that we will obtain, let me rub this step here. The expressions that we will obtain will be like the expressions will be, that's equal, we had HP vector angular momentum coming out equal, HP is equal, had it, okay, equal uh, M RPC cross velocity of point P plus integral of R cross omega cross R. This is what we are trying to solve. Okay. Now what I will do, in order to make it a bit simplified, let's assume for some time the velocity of this point P is 0. Okay. Let's say, for example, velocity of point P is 0. This we are assuming here. Later on, we will not assume Vp to be equal to 0. Okay. Let's first of all define the case when Vp is equal to 0. Velocity of the point P of the rigid body, velocity of the origin of the rigid body is 0. Okay. Let's obtain the angular momentum in that very case. And later on, let's not assume that Vp is equal to 0 and again obtain the expression for the angular velocity. Now, if Vp is equal to 0, which mostly is the case for our problems, or which we'll be discussing later on, the second case for it, HP then becomes equal integral of R cross omega cross R. Now, this is quite easy to solve, okay? But I'm recommending students that this assumption should not be taken as a rule, okay? This is a case. So I can write here case 1, Vp is equal to 0 and obtain the expression for angular momentum. And in the next case, assume that Vp is not equal to 0 and again obtain the expression for the angular momentum. Okay. Then, okay, let me write here case 1 in order to not create a confusion that it may be a rule. Case 1, when Vp is equal to 0, then HP is equal to this. Then using this expression, using this identity, we can write this as, this is equal integral of, integral of, this is integral of, integral is outside, this is our A, this is our B, this is our C vector. So first is A dot C. A dot C means vector R dot product with C, that is R. R dot R multiplied by vector B, that is omega. Fine. Minus A dot B, that is R dot omega multiplied by C, that is R vector. We'll cross it, we'll close it, and it is dm. Okay. Now when we try to solve it, the procedural code is like this. The angular momentum will become, integral of R dot R. We know R is having 3 components, xi plus yj plus zk cap dot product with xi plus yj plus zk cap. Okay, dot product between these two vectors. I need to place one more bracket here and multiplied by omega. Okay, omega is having three components: omega x I cap plus omega y j cap plus omega z k cap. It's having three components, right? Okay, then we have the minds. I will write this minds here. Then we have r dot omega, that is xi plus yj plus zk cap. Dot product with omega, that is dot with omega, that is omega x I cap plus omega y j cap plus omega z k cap. And we have our own multiplied by, this entire is multiplied by r vector. So we have r dot omega, we have done it, and multiplied with the, we have to multiply it with the omega, and that will be, we are multiplying it with now r vector, that is r is equal to xi cap xi cap plus yj cap plus zk cap. Okay, close our entire vector, that is then dm, that is fine. Okay, after writing this equation in this form, we can simplify it further. We can write this as this can be written as, now this we can write as integral of, we have this, so we have x into x is x square, so this will be, okay, x square. This is I dot I is 1, we know when you dot product this will be x square plus y square plus z square. Okay, the dot product between these two will be x square plus y square plus z square. Then we are multiplying it with omega x I cap plus omega y j cap plus omega z k cap plus omega z k cap. Okay, this is fine. Then we have minus expression. This will be, this is x, and this will be x into omega x, y into omega y, z into omega z. I will write here this x omega x plus y omega y plus z omega z plus z omega z multiplied by xi plus yj plus zk, xi cap plus yj cap plus zk cap, and dm. Fine. Okay, this is fine for us. We can now rub this expression. Okay, we can now wind it up in simplest steps. We can furthermore solve it. Angular momentum of a rigid body in 3 dimensions. The equations seem to be very lengthy, but after all, they are not. So now we can write this expression as, this is, we have to multiply x square plus y square plus z square with all these equations, okay, with omega x I cap, omega y j cap, omega z k cap. Okay, so I can simplify it and write it directly now. Rest I will leave as an exercise to the students to perform few more steps. I will leave as an exercise to the students to perform the steps themselves. The steps that they have to perform is to multiply omega x with x square, write down integral, then square bracket, x square omega x plus x square omega y plus x square omega z. Okay, x square omega x I cap, x square omega y j cap, x square omega z k cap, so on and so forth. Similarly about y square omega x I cap, y square omega y j cap, y square omega z k cap. Similarly about z square, same you will do here. Okay, this I am leaving as an exercise to do these multiplications yourself. The final expression that you will obtain, angular momentum of a body about p, you can then write them as, you can write this as, this can be written as omega x, since angular velocity we are assuming to be constant, angular omega x integral of y square z square dm, the y square plus z square, y square plus z square dm minus omega y integral of xy dm, xy dm minus omega x omega z integral of xz dm, and this will be along I cap. Okay, you have to first multiply them and take all the I components on one side, they will be these components. Okay, plus minus omega x integral of xy dm plus omega y integral of x square plus z square dm minus omega z integral of y z dm. This is along j cap. This will be along j cap. Okay, what we are doing, we have multiplying these and we are getting I component, j components and z components on the same side. The last one will be plus minus omega x integral of xz dm, xz dm minus omega y, minus omega y integral of yz dm plus omega z, plus omega z, right here, plus omega z integral of x square plus y square, x square plus y square dm, and this will be along k cap. Okay, so this expression represents is equal to angular momentum of a rigid body about point p. Okay, though we have to perform few more steps to further reduce it, to find what these integrals mean to us, okay, and obtain them in a form, that's what we call as a vector form or a tensorial form. But important is that we need to multiply these terms and separating these I cap, j cap and k cap terms on one side and obtaining this expression. Okay, so once we obtain this expression, we need to identify what this integral x square y square plus z square dm. What does this integral x y dm mean? What does this integral x z dm mean? Okay, we need to, these integral terms we need to identify. We have already identified them in the previous lectures of kinetics. So we'll be just substituting them what they actually mean to us. By the way, this means moment of inertia along x-axis. This means the product of inertia about xy axis, and this means the product of inertia about the xz axis. This means the product of inertia about xy axis. This means the moment of inertia about y axis, so on and so forth. From here onwards, we'll continue in the next class to further simplify this equation of the angular momentum, and then using this equation to obtain the equations of motion of a rigid body. Okay, so to obtain, we'll be using this equation to obtain the equations of motion of a rigid body. Then onwards, we'll be talking about the solutions of those equations of the rigid body in terms of its two solutions, the steady precession and the gyroscopic motion, in the coming up classes. This is all for today. So in the next class, we'll be further reducing it and going ahead. Thank you very much.